Broadcast is now starting. All attendees are in listen-only mode.
All right, so hello everyone, and welcome to today's SANS Mic presentation. I'm happy to see quite a bit of people coming, and I hope that about next 50 minutes to 1 hour will be interesting to everyone, where I'll talk about some weird and some maybe not so common web and mobile application vulnerabilities. And I'll try to make it as interesting as possible, as I said, for next about 50 minutes. So let me introduce myself. In case you wonder how to pronounce my last name, that's one of the jokes I always have to use because it looks as it's encrypted, but it actually is not. So my first name is easy, it's Bojan. My last name is Zdrnja. That's a bit more difficult. So if you can't pronounce it, don't worry about it. I'm one of the SANS Internet Storm Center handlers. As you probably saw, this presentation was and is scheduled to be at the same time as SANS Fire. Unfortunately, we were not able to be there in person this year, but I hope that our online time will be as good as if we were there live. I'm also a certified SANS instructor, so let me just introduce myself quickly and tell a little bit about myself, and then we'll dig into some interesting web and mobile application vulnerabilities. I'm currently serving as CTO at a company called INFIGO. We are based in Croatia in Europe. And I'm leading our penetration testing team. So some of the things that I will talk about and show today will be actually related to some interesting vulnerabilities that we found throughout years of testing various applications. I'll actually show some of the things live as well. So let's hope that all the demo gods are happy with me today, and everything will work as intended. We'll see in about 15 or 20 minutes. As I said, I'm a certified SANS instructor. I teach the SEC 542 course, which is web application penetration testing and ethical hacking. I'm also one of the co-authors of the course with the latest update that we did. We added quite a bit of interesting things to the course, specifically insecure deserialization, which I think is a cool vulnerability. Not one I'll talk about today, though. There'll be other things that we will cover today. As you can see here, I'm addicted to GX certificates. I know that people have more than this. I actually met quite a bit of them, and it's always like, wow, I need to work more on this. And finally, as I said, I'm one of the Internet Storm Center handlers. There's the URL that should be in everyone's bookmark, I hope. And even if you don't visit the web page, I always like to mention Johannes' podcast, Stormcast, that he does every single day. And this is something that I always like to listen to when I commute to work. Maybe a little bit less these days because we tend to commute less due to the COVID-19 virus, but still, it's a very, very good podcast to listen every single day. It's relatively short, only about 10 minutes, and Johannes does cover everything that's important in the security world that happened in the last 24 hours. So it's a really nice thing to listen to keep up to date with what's going on. So enough about me, and let's see what I will talk about today. So for this presentation, I decided to pick 4 different categories of vulnerabilities that are maybe sometimes a little bit underestimated. I'll first talk about finding some hidden parameters, something that I see that penetration testers often ignore, but sometimes we can actually use that to find quite a bit of interesting vulnerabilities. Then I'll talk a little bit about JSON Web Tokens, JWT. Something that became quite a bit interesting in the last couple of years, and especially in the last few weeks. If you were reading the news, there was a really interesting hack with JSON Web Tokens with Apple ID, where there was a hefty bug bounty delivered to a security researcher. So I'll go through some well-known and some maybe not so well-known vulnerabilities with JWTs. I also have a live demo. So I'll try to explain one interesting vulnerability that has been known for a little bit, but people sometimes don't understand exactly how it works. Then we'll switch to my favorite category of vulnerabilities, business logic vulnerabilities, and I'll actually show a couple of interesting vulnerabilities there as well that we found through some penetration tests we did. You'll see how actually they are easy to understand, and I guarantee that absolutely everyone will understand how those vulnerabilities that I will show to you work. And at the same time, you will see how devastating that they can be, sometimes much, much worse than even remote code execution vulnerabilities, because with business logic vulnerabilities, we can actually do some real impact to our target applications. And finally, we'll spend some time talking about mobile application vulnerabilities. Again, I'll show some, I think, interesting vulnerabilities in mobile applications, and I'll also show how to actually test and exploit such vulnerabilities. So as always, let's start with maybe the simplest thing, which is related to parameter identification. The next section of the presentation will be about how we find parameters which are maybe not obvious to us. So first of all, why do we want to find such parameters? Well, whenever we are testing for some security vulnerabilities, typically the most interesting part of any application is to see what input that application is actually receiving from us and how the target application is handling that input. It doesn't matter if you're testing web applications or mobile applications or even fat client applications. What we want to do in all of these cases is to actually somehow sit between whatever is on the client side and whatever is running on the server, so we can actually inspect and intercept the requests which are being sent from the client to the server and the responses which are being delivered back. So for web and mobile applications, this is more or less straightforward. As long as we can sit between the client-side web browser or a mobile application and the server, we will see typically HTTP requests. And these requests will typically contain a number of parameters that will be used to deliver something to the server-side application. So we could actually argue that every single vulnerability that we talk about is some kind of an input validation vulnerability, because it always boils down to some input which is being sent from the client to the server side of the particular application we are testing. So for our web and mobile applications, typically our input will be delivered via get or post parameters. It doesn't matter if this is like a normal HTTP request line parameter, or maybe it will be some kind of a JSON object or an XML object that is being sent in a particular request. Our goal will be always to find those parameters, identify them, and then basically fuzz them. Well, to be honest, what I just said is how web application security scanners work. All they do is they try to crawl or spider the target web application, identify every single endpoint, then find all parameters that those endpoints accept, and then try to fuzz them to see how the applications will behave when we are sending perhaps unexpected input to those identified endpoints. So let's take a look at one example that we can see on the following slide here. So here we can see a very simple GET request that is going to some kind of an API, and this is quite commonly used. So quite often we can see web or mobile applications these days that will consume some APIs. This could be actually a web service, a RESTful web service. But in this particular case, we can actually see in the GET HTTP request line that there is a relatively big number here. It's not too big, right? But this number is probably something that is being used to identify some kind of an object that is being then consumed by the application on the server side. So we already have a potential vulnerability here, but this is not something I will talk about in this particular part of the presentation. But just keep in mind, obviously, that we could have an insecure direct object reference vulnerability here, a door vulnerability, because if we intercept this request and if we change the number that is being passed in the GET HTTP request line here, we could maybe get another user's transaction, because this API obviously will give back a list of transactions for a particular user. So this is definitely one potential vulnerability we will test for. But since I'm talking about parameter discovery, what we'll be interested in is a possibility of actually appending parameters to this particular API, which will maybe make that API behave differently. Now, how do we find those parameters? Well, if we are testing a web or a mobile application, and if there is, for example, a screen or a web page that allows us to export data in CSV format for this particular API here, then it's kind of straightforward. We will click on that particular button, wherever it is. Maybe it's in, in our web browser, maybe it's in our mobile application. We will see this request being passed through our interception proxy, and it will be easy to know that this particular API accepts a parameter called export with the value of CSV. Now, if we don't have such a web page or a button in our mobile application, then it might be a bit more difficult to enumerate or identify this particular parameter. We might have to shoot blind in order to guess this. Now, this is what I will talk about in this part, parameter discovery. How do we find parameters that we actually don't know about? Whenever you see something like this, export equals CSV, obviously I would modify this parameter and just try to see what will happen if I change this to maybe export equals PDF or something else, TXT, or whatever other format I think that the application might be processing. It is always worthwhile to check for this, because even if there is something that doesn't allow us to be selected initially from the web page or from the mobile application, there might be something implemented in the application which might not even be finished. So we could provoke some errors that will help us in identifying other vulnerabilities. So how do we find those hidden or secret parameters? Well, there are a couple of tools that I like to use when I do my penetration tests, and obviously, as I think the majority of or maybe even all penetration testers use the burp suite, which is the de facto standard interception proxy today, one that we also use in the SEC 542 course. There is a really nice add-on that you can download and install from Burp Store, which is called Paraminer. This particular add-on will allow you to just select a single link, and then you can run a scan. So the extension will actually try to identify any parameter that might exist in this particular request that will be processed by the target application, and it will try to be as efficient as possible. You can see on this particular slide me running the extension against the isc.sans.edu website. So sorry, Johannes, but I needed a website to test with. And over here you can see that I'm attacking the contact.html link, and I'm trying to supply all sorts of different parameters with random values, so the add-on can actually check what will happen in the response, and it can identify if any of these values were actually reflected back from this particular request. If you don't want to use the burp extension, there are a couple of command line tools that can be used for this as well. Here are a couple of tools that are quite popular today. The Perm Spider or Arjun, which is another command line tool that you can use to identify parameters that are maybe not visible initially, that are potentially hidden. These two tools come with their own lists of parameters. So for best results, you can actually use Daniel Missler's fantastic sec lists. So these lists can contain well-known or common parameter names that we can use in order to identify any of the potentially hidden parameters that the developer maybe didn't want us to know about. So the procedure that both of these tools will actually use is very, very simple. We first have to supply the endpoint that we want to attack, and then the tools will first send one request with a random, hopefully non-existing parameter, just to figure out how the application is behaving with such a parameter, and then they'll start fuzzing the application like there's no tomorrow. They will simply take all of the parameters, similarly to the paraminer extension for burp, and just populate those parameters with random data to see if anything is reflected back, or maybe there will be some kind of an error displayed or something similar to this. So you can see here a couple of examples that actually worked in the real world. And yep, if you thought that admin equals true is too simple, it actually is, but don't underestimate simple vulnerabilities, because quite often we can see them working, and why bother, going through some heavy digging when something like a pending role equals admin in our request will actually work all the same. So a couple of these that you can see here can be found more often, but it's always worthwhile on checking for parameters that we don't know about. So with this, I just wanted to warm you up a little bit, because if this seemed too simple for you, then don't worry, we'll now jump to more interesting and more complex things. So the next section about maybe not all that commonly checked vulnerabilities will be related to JSON Web Tokens. And if you don't know anything about JSON Web Tokens, again, don't worry. I'll go through all the details, and we'll do some things live. So let's see how lucky I am with live demos. It's always fun when it works. When it doesn't work, maybe not so fun, but hey, at least we'll try. All right, so what an epoch timestamp of when the particular token was issued. We can have the issuer name, we can have the expiration time, and so on and so on. As I said, we can have custom claims as well. So we can put something like logged in username, which will be the username of our current user stored in the token. The goal of the token is, again, to assert certain claims. So obviously, we will need to protect those tokens properly. So once they are issued, it should not be possible for an attacker to modify the content of a token, because otherwise they can basically do whatever they want with that token's content. So JSON Web Tokens, JWT, which are used most commonly with web and mobile applications today, are technically JSON Web Signature. There are also two other tokens we can use. So we have JSON Web Encryption and JSON Web Key. So JSON Web Encryption simply is used to transfer JSON-based data structures which are encrypted, and with JSON Web Key we can actually represent a key in that particular JSON structure. We will be talking about JSON Web Signature, which is what JWT is today. So let's see how this works and how it can be normally used and, of course, protected. So JSON Web Tokens are relatively simple, and they consist of three important parts. At the top or at the beginning of our JSON Web Token, we have a header, and the header will typically define the signature algorithm and the type. The type here will be JWT. This is what we will be using. And for the signature, there is a number of different algorithms that are supported. There's literally like 24 of algorithms that are supported, but with majority of applications that I've been testing so far, and I think that those of you who do the same thing will agree with me. So for the majority of applications, typically we see one of these three which are shown on the slide. So most commonly, we will actually see HMAC with SHA-256. So this is like a hashing algorithm with a secret key that can be used. Then we'll typically see RSA signatures with SHA-256 as well, which is RS-256, and sometimes, but a bit rare, we can see elliptic curve with SHA-256 used as well. As I said, there's a number of other algorithms that are supported by the standard, but these three are most commonly used. Notice the last one, none, which is obviously really bad, something that we shouldn't be using. We can use that algorithm as well, which means that there is no signature whatsoever. And luckily, the majority of frameworks or libraries that are used for handling JSON Web Tokens today will actually not allow you to use the none algorithm out of box. You will actually have to go and enable it manually if you really want to use it. That just shows to us how bad none is. So let's see what else we have in a JSON Web Token. We have the payload, and the payload defines the assertion, and it contains our claims. As I mentioned previously, we can have those claims which are defined by the standard, or we can have whatever claims we actually want. So a developer can add whatever they want in a particular JSON Web Token, and we can see here that we have two non-standard claims, the role and the logged in username. And obviously, I'm pretty sure that everyone that is looking at this particular slide right now thinks about how cool it would be to change the role field, the role claim from role user to maybe role admin, and see what will happen in that particular case. Well, it shouldn't be that easy to do this in a token. So that's why we have the signature at the end of the token. And the signature actually prevents us from changing this role claim to something else. So how is the signature calculated? Well, it's actually relatively simple. What we do in order to calculate the signature is take the header, and remember the header just typically contains those two fields, algorithm and type. We base64 URL encode the header. We take the payload, again, base64 URL encode the payload, concatenate these two values with a dot value between them, with a dot character between them, and then perform the HMAC SHA-256 with a secret key, in case this is the algorithm that is being used on the full value. And this is how we get the signature. Now, this token can be passed to our end user, and every time that end user tries to access the a potentially sensitive endpoint, the server-side application should take the value from the JSON Web Token. It will take the header and the payload, which are again just base64 URL encoded. We can see what's in that value, but the server side will calculate the signature, compare it with the signature that was delivered from the client, and if they don't match, then the server side will know that someone tampered with the token, so it is an invalid token. If we want to create it with Python, for example, and this is what I will use in the upcoming demo as well, you can see here on the screen that it's really easy to do it. All I did here was to import first the JWT library, then I just created a dictionary in Python called JWT param with one single claim, username, and value of Bojan Z. And finally, I call the encode method from the JWT library with the body with my claim, the secret key, which will be SANS fire, all uppercase, and I specify the algorithm, which will be HS256. So it's a HMAC SHA-256 algorithm. Finally, you can see that in the encoded variable, I actually have my JSON Web Token. Notice that there are three parts of the token. They are separated with a dot character. So the first part is obviously the header, the second part is the payload, and then I have my signature. Now, if I want to verify it, I can try to decode it, and if everything is okay with the signature, my decode variable will contain the claim that I initially put, and as you can see here, everything is fine and good, and it all works okay. And this is how it's actually used in an HTTP request. You can see the request at the bottom of the slide here. This is an authorization request header, which contains the bearer token, and we simply have the the JSON web token in this particular bearer authorization header, and this is then delivered in every single request to the target web application, either by our web application or a mobile application, doesn't matter what it is. And with every single request, the server side will verify if this bearer token is valid or not, just by checking the signature on this particular token. Not too complex, right? This is relatively straightforward. So let's see what issues we have with JWT tokens. There are a couple of typical vulnerabilities that are being abused whenever you see a JSON Web Token, and this is definitely something that we should try abusing whenever you're testing an application that uses this. So first of all, we can have algorithm confusion. What is algorithm confusion? Well, as we can modify, obviously, the header and the payload, we can't modify signature. If you remember from a couple of slides before, there is a very weak algorithm that is used for signatures, and that algorithm is called none. As I said, again, modern libraries should not use that, but it's always worthwhile checking if our application actually supports this algorithm. So it's very, very easy to test for this. All you need to do is just to strip the signature and change the algorithm from whatever it was, for example, HS256 to none, and then see if your target application accepts your token. If it does, then you have a critical vulnerability, because you can forge tokens now, since they have no signatures that can be checked by the server side. Hopefully you will not see that, because libraries and frameworks will actually prevent people from using the none algorithm when creating tokens. Besides this, there are a couple of other potential vulnerabilities here, so let's see what they are. If we are using the HMAC algorithm, the HMAC SHA-256 algorithm, then obviously we will have the signature with the token. But notice that if we receive one single token, basically we have all the material that we need in order to crack that particular token. So just by having one single token, we can actually try cracking it, because all we need to guess now is the secret key that was used in the HMAC SHA-256 algorithm. So let's see what we can use for that. Obviously, this is something that people have been doing for some time already, and this allows us to use any of these two popular cracking programs. So both John the Ripper and Hashcat support JSON Web Tokens, and you can actually try to crack the secret key that was used in order to create that one token that you have with any of these two programs. If you use John the Ripper, just make sure that you have the jumbo patched version, and all you need to do is store your JSON Web Token into a file and then try to crack it. You can do the same thing with Hashcat, so all of those nice cracking rigs or Bitcoin mining rigs that you have can be also used in order to crack JSON Web Tokens as well. This is also very, very dangerous. So because like if you crack the secret key, then there is nothing preventing you from issuing any token you want, and it's actually game over. This is keys to the kingdom. So obviously, whenever you test an application that is using JWTs, always try to crack them. It will typically be limited time that we can spend on trying to crack this secret key, but it's always worthwhile testing it, because you might stumble upon a really weak key that was maybe set originally by developer, and then they forgot to change it later to something that should be really, really long and strong, and it shouldn't be absolutely possible to crack this key, because as I said, once we crack it, it's game over. We can issue whatever keys we actually want. So besides this, there are two more categories of vulnerabilities that are typically exploited with JSON Web Tokens, and the one I really, really like was originally posted on Auth0 website, and this is an interesting bug in incorrect verification of tokens that was actually identified in many libraries, and there are still some libraries that are vulnerable to this particular vulnerability. And specifically, if you hear any of the developers that they are rolling their own libraries, or they developed their own ways of using JSON Web Tokens, definitely test for this if you see them using RSA-based algorithms for verification of JSON Web Tokens. So this is how the vulnerability works, and I'll demo this to you live, because I think it'll be the easiest to understand once you see how it works live. So this is the attack. So when we use the RSA-based algorithms in order to sign JSON Web Tokens, we use the private key in order to sign it, and then we use the public key to verify if the signature was correct. It makes sense, right? Private key to sign it, then the public key to verify that signature. This makes sense because the private key will be known only and exclusively to the server. When we get the token back, then the server will use the public key to verify if the token is okay. Now, the vulnerability here is in the fact that we can actually use the public key, provided that we get it, but hey, it's the public key, so typically we shouldn't worry about the public key. It can be broadcasted to everyone. So when exploiting the vulnerability, we will use the public key to sign the token, but we will change the algorithm to the HS256. So if the developer didn't specify the signature verification algorithm properly, we might actually fool the application into thinking that it got the proper token. Now, this is a little bit difficult to explain in words, so I think the best thing will be to actually jump into a live VM and actually demo to you how this works, because these couple of seconds will make it way more easy for me to explain everything. So hopefully you can see my VM right now, and I think that you can. So let me do the following. I will actually first create a private and public key pair by using OpenSSL. So I will just do OpenSSL genRSA, and over here I will just store it into private.key. All good. Now I will use this private key to create the corresponding public key. So again, I will use OpenSSA, RSA. I will read the private key. I will store it into public key, and I will just tell OpenSSL to store public key into this particular file. So now we have both the private key and the public key. Let's take a look at them. So this is our private key, okay, a nice long blob that contains the private key, and I can do cat on public key, and we can see another blob over here which contains my public key. So in the other screen here, I will just use Python. Actually, I want to use Python 3, sorry. I killed the other window, that's okay. I'll just need it over here for something. So let me start Python 3, okay. I will import the JWT library so I can create tokens easily. And now I want to create two variables that will contain my private and public keys. Normally in a real world setup, I would just read this from files. What I'm going to do here is I will just create two variables like this, and I will simply copy and paste things from private.key and public.key like this. There we go. So instead of reading it, I'm just copying this into a file over here. All right. And I'll do the same thing for public key. So let me do cat on public.key. There we go. Copy and paste that. Paste it over here. And now I have the public and private key. So let's see how I can create a legitimate token. So I will create my assertion here, or let's call it claim. It will be something like this, username, and I will put myself as a user. So this will be in our claim. And all I need to do now is, I'll put this into an encoded variable. I will call jwt.encode with my claim. And now I will use my private key. And as algorithm, I will use RS-256. Okay, so again, what this will do is create a JSON Web Token containing this particular claim, which says username Bojan Z, and we will use our private key with the algorithm RS-256 to create that JSON Web Token. So here it is. Remember, we have the first part, this is the header up to the dot. Then we have the second part, which is the body, again up to the dot. And then all of this is our signature, our RSA signature. Now, when this is being sent to the server-side application, in order to verify it, we have to use the decode function, and we have to provide the public key, because with the public key, we will verify if this is okay. So let's do that. So I will do decoded equals JWT decode. Then I will here put the encoded content, the JSON Web Token. I will use the public key to decode the key. And now I don't need to specify anything else because the algorithm is specified in the header. Remember, the algorithm tells the server side what algorithm was used to sign that particular JSON Web Token. So when I do this, in the decoded variable, I can actually see that I have my body, and it was all good. So this particular claim has been verified correctly. Now, remember our attack vector. The attacker knows that we are using RS-256 because obviously we can see that from the JSON Web Token header, and the attacker has the public key. So this is not that unusual, right? Maybe it is the public key that we posted somewhere so everyone can verify the tokens or something like that. So let's say that the attacker has that public key, or they obtain it somehow. Again, this is not something we should really guard. So this can be sometimes easy to get. So what the attacker will do is the following. First, the attacker will change the claim. So instead of username Bojan, the username will be admin. Hey, we want to be admin, right? Now, the attacker will use the same function as I did. So we will put this into encoded, JWT encode. So we will encode this particular claim, but here we will use the public key. Remember, the attacker doesn't have the private key. They only have the public key. So they will use the public key to sign this token, but they will put the following algorithm. They will use HS-256, which is HMAC SHA-256 algorithm, which takes a secret key. It doesn't use a certificate. It actually uses a secret key to sign the token. So what will happen here is that our claim will be actually signed by using the HMAC SHA-256 algorithm, and the public key will be the secret key. So the public key, which was in the PEM format, as you saw previously, it is just a plain text string. It will be used as a secret key. So once we do this, we get our nice encoded JSON Web Token. Notice that the signature is much it's not as long as the previously used one, but it is a valid signature for this particular token. Why valid? Because if this is what the developer did, again, encoded public key, notice that this is same as the previous line I had over here, because that's what the developer did. The developer is expecting that they will receive a JSON Web Token signed with a certificate, with a private key. They're trying to decode it with the public key now, and what will happen is that we will get no errors because the JSON Web Token library will try to figure out what the algorithm is from the header, and the header will say what? The header will say that it is HS256, and the library will simply try to decode this easily with whatever algorithm was specified in the header, and with the public key as the secret key, and this will actually work. The fix for this is very easy, and all that the developer needed to do was to specify here algorithm like this, RS256, to hard code the algorithm that they are expecting. And now when we try to decode it, obviously we will get an error because the algorithm value doesn't match the one which was in the JSON Web Token, and this would indicate to the developer that something bad happened with the JSON Web Token. So I hope everyone understood this. It's actually, when you just juggle a little bit with this, it's not all that difficult to understand, as you can see, but it can be extremely devastating. And it is just one simple programming error where, when calling the decode function, the developer actually doesn't supply the algorithm that they are expecting, and then it will simply be taken from whatever is supplied in the JSON Web Token. So let's move on, because we have more interesting things to talk about. Finally, the last vulnerability that is sometimes exploited with JSON Web Tokens is related to JSON Web Token reuse. Now, with modern applications, quite often we can see that they use microservices. And in microservices, you can have many entities, many endpoints that will be accepting the JWT tokens that are being issued by another entity. Now, an attacker can always try to use the issued token and then maybe submit it to a different service. If the different service is trusting the same issuer, then the token will generally be valid. Now, depending on the claim, it could be something that the service is not expecting. So you could get all sorts of different errors, or you could provoke strange behavior from that microservice. What we can also do is, for example, use a token that we have been issued with, and then change the workflow of the target application. If there are a couple of services that should be called in order, we might try to change that order, but with a valid token, to see how the application will behave. And this is actually a business logic flaw, something that will move on as the next section of my today's presentation. So as I said here, pure love, because business logic vulnerabilities cannot be found by any tool that we use today. So on one side, this is kind of job security for us in the penetration testing field, and that's always a cool thing to have. So let's see what we can do with business logic vulnerabilities. And I'll show to you two interesting business logic vulnerabilities, again, that will be very, very simple to understand, but I hope that they will challenge you to look more for such vulnerabilities. So what are business logic vulnerabilities? Business logic vulnerabilities exist whenever there is a legitimate processing flaw or workflow of an application that we somehow modify, and that actually results in some negative consequence for the particular application or organization. In a lot of cases, these are the most devastating vulnerabilities that we can find. So imagine this, you get to pick one. You found a SQL injection vulnerability in an internet banking web application, or there is a business logic flaw that allows you to perform arbitrary transfer of funds. Which one would you pick? What do you think is more devastating? Well, probably the second vulnerability, because when you have a SQL injection on an internet banking web application, which has a huge database in the backend, well, it can be difficult to use that particular vulnerability. So the business logic flaw is actually more devastating here. As I said, these vulnerabilities cannot be scanned for automatically, so tools simply do not understand the logic that is used in the application. So this must be tested by a human, by a real penetration tester. So this is the example that we use in SEC 542 in Web Application Penetration Testing course. to easily explain business logic vulnerabilities. So we can see here a normal grocery shopping workflow where we just get some food to our shopping cart, add more items to our shopping cart, scan them, and then we pay for our groceries, and all is good and nice. With shoplifting or with someone exploiting a business logic flaw, they might add some food to the shopping cart, scan for groceries, pay for them, and then add more food in that shopping cart, and they're exploiting a business logic vulnerability if there is no guard in that particular shop to actually stop them and prevent them from doing so. This is how we can exploit business logic vulnerabilities in the real world as well. Whenever we have a workflow that is simply flowing through an application, it's always good to try to modify that workflow and see how the application will react. So here are two vulnerabilities that I want to share with you. They were both found during some penetration tests. The plugin allows them to automatically calculate the final price in their particular currency, so it is easy to use. However, there was a bug in the plugin that actually manifested when there was no specific currency specified by the site administrator. So when this was configured, and when an attacker changed the currency, if that currency is not specified on the server side, the application would simply fall back to the default currency. So in other words, what we were able to do is to modify the currency, for example, from US dollars into Japanese yen. And then instead of paying 1,000 US dollars for something, you would end up paying 1,000 Japanese yen for the same item. And this is kind of cool because you'll pay only $9. And over here, you can see how easy it is to exploit this vulnerability. All we need to do is specify a currency that is not set correctly by the website administrator, and then the application will automatically calculate the price, which will end up, so we will end up paying less for that particular item. So this very, very expensive leather jacket of $5,000 was actually, we were actually able to purchase it for 5,000 yen, which is way, way, way less. Now, sometimes it is not all that obvious. So I wanted to show another interesting example to you with another business logic vulnerability that actually took me quite a while to find out. But I think it's kind of a cool example of how we can shuffle data and then get unexpected results. So this was the case. The case was when we have a web shop, a credit card processor, and the user. So when you are visiting your web shop, you put your items into your cart, and then once you click on checkout, when you want to pay for the cart, typically you will be redirected to a credit card processor that will take your credit card information. This makes sense because most web shops don't really want to handle your credit cards. So they will redirect you to a credit card processor, and once you pay, you will be redirected back so you can finish your purchase. You can maybe set your delivery address and so on. I'm sure everyone has used such systems before. Now, this is a complex thing because we have to somehow let the web shop has to somehow let the credit card processor on how much to charge the person for. And there are two ways to do this. We could do this out of band. So a web shop could send a message directly to the credit card processor and tell the credit card processor, hey, for transaction 123, please charge $1,000. Or we could do this while redirecting the user's browser to the credit card processor. Now, the user could intercept the request and modify the price. So we want to prevent the user from doing that. And this is typically done by using HMAC. Hey, Same thing as with JSON Web Tokens. So the web shop and the credit card processor share the same secret key. And this secret key allows them to calculate a hash, which will preserve the integrity of the requests. So let's see what this looks like. Here is one such example, and this is easy to understand. So it is a post HTTP request to a checkout web page. We have a couple of parameters, the merchant ID, transaction ID, amount, which is $111.23, and we have a nonce, which is a random number, which is there just to prevent replaying attacks. So how do we prevent this particular request from being changed? Because remember, if I intercept it, I can change the amount to anything I want. Well, we use a simple HMAC algorithm over here. So we have our secret, which is secret over here. And in this particular example, we are just using MD5. It doesn't matter. Typically, this will be a stronger hashing algorithm. So we take all of these parameters, concatenate them with the secret keyword as well, calculate the hash, and supply that as the last parameter called hash. So this is done by the web shop. Now, when this request arrives to the credit card processor, the credit card processor will do the same thing. They will take the merchant ID, transaction ID, amount, and nonce, concatenate them, put the secret keyword, calculate the hash. And if the hash is the same as the one that we received, then there was no tampering with the data. And it all is great and good. So it looks like this cannot be easily circumvented, but pay attention to parameters here. They are concatenated one with each other, which means that if we intercept this request and then carefully flip this like this. So notice what I'm doing. Let me change the slides. I'm just taking the last 3 digits from the amount and I'm moving them into the nonce parameter, which is a random number. So it is not actually checked. It is just checked for replaying. Now this, when being concatenated, will actually result in the same hash. And I change the price to 11 cents without breaking the hash. So the credit card processor will believe that this is the correct price and I will be just charged for it. And this is another example of how business logic vulnerabilities can be really devastating. Sometimes it takes a bit more thinking on how to find them. And I was able to find this because I had the source code of the application. Otherwise, I wouldn't be able to find this easily. All right, so let's go to the last section. I just have about 8 or 9 minutes left. So I'll just show a couple of vulnerabilities here, and then we'll wrap it for, I hope, an interesting presentation for everyone today. So with mobile devices, things get quite a bit more difficult because now our threat landscape is actually has actually changed quite a bit, right? So now with those devices, we must pay attention to both data at rest on what's being stored on devices and data in transit, how we protect requests and responses from in-flight modification. There are many things that we have to pay attention to, and that's why we have a 6-day course about mobile application penetration testing. But keep in mind that whatever is done locally on a mobile device can always be attacked by an attacker, right? Because no matter what obfuscation or similar protection mechanisms we used, an attacker can always see that on the mobile device and they can always modify it. So whenever I'm testing a mobile application, I'll always like to pay special attention to any local authentication handling of that particular mobile application. So I always want to check the manifest, for example, to see what is being exposed, which permissions are used. And then if the application, for example, locally checks authentication, I always like to see how it handles my passwords or pins. Unfortunately, with mobile devices, since it's a little bit kind of difficult to enter passwords, a lot of applications and users will typically use pins, right? And those pins will be 4 or 6 digits. That's about it. Sometimes you can use things like ALP that you can see here. They are a bit stronger, not much better, unfortunately, because a lot of people, we used some of typical curve that you can see on this slide as well. So they are stronger, but they are not all that strong when comparing to pins. So let's see what we can do with applications here. Sometimes we have examples which are almost too obvious. So you can see here a manifest for an Android application that actually has an intent, which is a function, a method you can call on an Android device, which is called mobile.pinChange, which has no correct permission. So an attacker can simply launch the application, as you can see at the bottom of the slide, and actually call the pinChange function without any problems whatsoever. Game over. We can change any pin we want. Sometimes, depending on the applications that we can encounter, we can actually see different vulnerabilities that we wouldn't expect from mobile applications. So how about having a cross-site scripting vulnerability in a mobile application? Sounds like something impossible? Well, not really, because sometimes we can have so-called hybrid applications, which are becoming more and more popular lately. For example, if any of you are running Slack now, Slack is actually, well, some kind of a web application. It is built on Electron, which is a popular framework that uses JavaScript and HTML to create applications. We can have same applications running on mobile devices, which means that the methodology that we will use to test such mobile applications will be pretty much aligned to testing web applications as well. Besides this, as I said, whenever we see something being handled locally on the application, we can always try to circumvent that particular security control, because at the end, we do have full control over our mobile devices. So whenever we test a mobile application, besides things shown here, like testing if the application will verify if the device has been jailbroken or rooted, if there is certificate pinning, authentication handling, and proper two-factor authentication handling as well. If we see that the application is storing sensitive data locally, then, well, it's almost game over. It could be difficult to crack if there is obfuscation and other security mechanisms being applied, but it could be relatively simple as well. So for the end, let me show you one interesting example and how we approach this. The slides will be posted later on the SANS website, so you can check the source code over there as well. So this was the example that we were testing. So when the application was started, it asked the user to enter a PIN, and as you can see here, there were only a couple of attempts remaining if an incorrect PIN was being entered into the application. Now, whenever you see something like this, that always check if there is any network traffic being generated by the application, because if that PIN is not verified on the server side, then it's stored somewhere locally, which means that in theory, we can find that PIN. We could reverse engineer the application completely to see how it stores the PIN, or we could try to guess it. Now, reverse engineering can take a lot of time, so that's why I like to apply dynamic instrumentation, and the absolutely best tool for that is called Frieda. So what is Frieda? Frieda is a dynamic instrumentation framework that works on absolutely every platform, Windows, macOS, Linux, but also Android and iOS. And it allows us to inject snippets of JavaScript code into native applications on these platforms. So this allows us to inspect what is happening in a function. It also allows us to fake a function's result, which is kind of cool. So we can inject this into our mobile applications and then change how the application actually behaves. So remember the example from the slide before. Let me just jump that quickly. Obviously, this application is testing for the PIN locally, and there is some kind of a counter that will prevent me from entering the PIN if I enter wrong PIN, for example, 5 times. So what I will want to do is try to enter all possible PINs, but find that counter and then reset it after 3 times so I can try more and more. And this is how we do it with Frieda. We basically just write some JavaScript code that will hook 2 functions. The first function I want to hook is the function that will allow me to guess pins, you can see that on the slide here. As I said, slides will be available later, so you can go through the code and see how to do it. There are also many repositories with Frieda. A lot of pen testers do this, so if this is something that you do, it's actually easy to find that code. So here, what you can see, the most important part is that in the for loop, we actually loop from 1 to 9999 just to guess what is our pin. Then we also need to reset the counter. So the most difficult part of the pen test here was to find where this counter is being stored by the application. So we just wrote another function called reset counter, and then after every single brute force attempt, we reset the counter back to 0, and you can see that being done at the bottom of the slide. So once we execute this application, ta-da, after some time, we actually get this nice screen, which tells us what is the correct pin of the application, because we can check what was the output of the function that was used to verify the pin. We can check if the output is something like OK or not. In this particular case, there was an exception raised, so we either caught the exception. If there was an exception, we know that the pin was incorrect. If there was no exception, we know that the pin was correct, as you can see on this screen. So just to wrap up, because I'm running out of time slowly, which is typical for me. If any of here took my courses, you know, I'm always struggling with time, but I at least hope that this was interesting for everyone and that I gave you some new ideas of what to look for when testing web and mobile or any sort of applications, really. So don't strictly look for technical vulnerabilities. They are cool, you know, but exploiting business logic flaws, sometimes I think that's kind of priceless. And not to mention that typically management will understand that much easier than, you know, explaining a blind SQL injection to them. And combine the best of two worlds to be as efficient as possible. Some of the vulnerabilities here are typically difficult to find if you are just performing a dynamic test. If you are performing a static test, then they might be easier to find. And finally, don't be scared about, you know, trying something that looks silly. Cool thing about pen testing is that there is nothing silly here, so we can always try whatever comes to our mind. And with this, I would like to thank everyone for the time, for staying here. As I said, copy of the slides will be available on the SANS website. If there are any questions, please let us know. Let me see on the over here. Maybe we can, provided I can. So there are some cool comments. Thank Dominic. Absolutely, there is a fantastic mobile testing guide from OWASP as well that I definitely suggest that you use if you are testing mobile applications. Let me see a couple of other questions here. So JSON Web Token in the wild with a vulnerable claim parameter that allow you to specify the URI of the key that was being used. I don't think I've seen that in the wild. Could be that such cases exist, of course, but I personally haven't seen it in applications that I tested. So let me see another question. Assuming that an attacker gains access to a mobile device, the attacker tries to abuse the device using attacks like power analysis, fault injection. Can they be prevented remotely? Remotely? So in such cases, typically what I would say is that if there is any way for us to have a logic that will prevent such attacks moved to the server side, this is the way that we should do it. So in the example of, before, with the pin being stored locally, typically when I find this, my recommendation is to never store such sensitive information locally. So for authentication, for mobile applications which are sensitive, I typically recommend that an algorithm such as Okra is being used. So we generate some kind of a one-time password locally. Then that one-time password is being sent to the server side, and the server side checks if it is okay. But what's important here is that every single pin that you enter generates a one-time password. And the only way to test for it is to actually send the request to the server side. So the server side will tell you if the one-time password is okay or not. This way, we will prevent local attacks, no matter what they are, because the only thing that the attacker will be able to do is try to enter a pin, get a one-time password, send it to the web, and check if it's okay or not. this allows us to lock that user, for example, after 3 incorrect attempts on the server side. And let me see if there are more questions here. Okay. How did I know what variable to search that control the counter reset times? So this is what I did when I reverse engineered the application. So I needed to reverse engineer it in order to find how that counter is being controlled. And then with Frieda, I was able to reset the counter after each attempt to brute force the pin code. In some of these cases, we actually need to spend some time reverse engineering. So what I'm trying to do here is to balance between reverse engineering and using dynamic instrumentation so I can be as efficient as possible. And let me see, we have a bunch of questions here. So yeah, so I basically just use something like JDEX. JDEX is a great tool that will allow you to decompile an Android application. So you can see some high-level Java code, which will make reverse engineering much, much easier. Another question, how do I use burp on an Android application? So you need to make the application send the traffic through a proxy. With older version of Android, this was relatively easy. You could just put your proxy into your device settings and the device will use your proxy. With modern applications which use certificate pinning, you will need to unpack the application, find the certificate pinning code, then either remove it or maybe add your burp certificate into that particular store, pack the application, and then install that application on your mobile phone. So it's getting more and more difficult. This is not all that difficult to do if there are no additional protections, but sometimes, again, I encounter applications that will check their integrity, so they will try to prevent you from doing that, so it can be way more time demanding. But there's always a way to do it because that application is running on a phone which is under our control. So at the end of the day, we can always actually do it. Question about Okra, can the Okra nonce be intercepted during onboarding process? Yes, it can. So for the Okra algorithm, we have to have the secret seed, and that seed must be somehow generated on both on the server side and on the client side, because that seed is used to generate the one-time password. So generated that seed is the most important part. So whenever we use such an approach, we need to correctly make sure that the seed is not intercepted by an attacker, because otherwise, if the attacker knows the seed, they can generate same one-time passwords as we do, so they can just authenticate as our target user. And probably the last question from Michael, did you use an emulator for Android Studio? So I prefer to use physical devices. There are a couple of reasons for that. First, they will be much faster than an emulator. So if you're dealing with a complex application, it will be really, really slow if you use it in an emulator. So a physical device will be much better. Second, some applications require certain parts of the device, so they will actually not work in an emulator. So it's best if you use just a physical device, and you can use it by being connected to via Android Studio and so on. But use the real device to test your mobile applications on. There is quite a bit of material you can find about that on the net, so just search for that, or of course there is the SANS course for mobile application pen testing as well. I don't teach that one, but it's a cool course. I set for it, so if you can afford to attend that, I would definitely recommend it. Let's see, one more. What all tests we can do in modern apps based on Electron? So generally, Electron should be quite restricted. So Electron shouldn't allow you to, for example, launch cross-site scripting attacks and stuff like that. There have been vulnerabilities in Electron-based applications. So I would suggest that just check for some of the previously identified vulnerabilities in Electron-based applications. In quite a lot of times, they were related to handlers for different URIs. So for example, when you put something like HTTP:// and you put a different handler, then you can abuse that through Electron. Electron is trying to fix and eliminate most of these, but they can still be a possible vulnerability. So I suggest that you check for previously found vulnerabilities and then see if they can apply to an application that you are actually testing. Nice, thanks, Michael, for the comment, and thanks everyone for a lot of questions. I hope that you enjoyed the presentation. As I said, the slides will be on. If there are any questions now or later, let me know. You can find my details in the presentation on Twitter as well. Bojan Z, easy to find me. And when you can, visit the Storm Center website as well, where I try to post interesting things, not that many as I would like to, but I'll try to do more. So thanks everyone, and depending on your time zone, have either nice afternoon or good night to you if you are in Europe. Thanks again for your time for the presentation. Thank you.